To find what the actual integral of x squared from 1 to 3 is, we need to graph the function x squared from 0 to 3. A thing worth noticing, our x-axis, so our graph needs to include the entire x values from 0 to 3. It doesn't need to include the y values. The calculator, when it graphs that, it worked out all the y values, and it's storing them in memory, even if they don't show up on the picture. 1 to 3 or 0 to 3? What were we doing? I don't remember what our function was. We were doing values between 0 and 3. So I want the integral from 0 to 3 of this function. I say second trace is calc, 7 is the integral from lower limit 0, upper limit of 3. We knew it was between 7.9 and 1015. It turns out the actual answer is 9. Cool. Just like with derivatives, occasionally it'll be a nice round number, occasionally it'll be some ugly decimal, and it's hard to tell exactly what number it is. But the good news is the calculator is going to give you lots of digits right away. So yeah, we got the actual value for our fly problem. The thing is giving us the area under the curve is the meaning of the integral. But the hard part is doing these Riemann sums. Let's do one more Riemann sum example. Okay, example. Let's approximate the integral from -1 to 2 of x to the 4th dx using delta x equals 0.75. Find an upper sum and a lower sum. These are the tricky ones. An upper sum, the point we choose to plug in, needs to be the one that gives the highest value on the interval. The lower sum, the point we plug in, has to be the one that gives us the lowest value on the interval. Most of the time, you have a function that's increasing, so the upper sum is the right endpoint sum, the lower sum is the left endpoint sum. If you're decreasing, it would be vice versa. Here, we're in the unfortunate circumstance that our function, x to the 4th, is not increasing or decreasing. X to the 4th looks kind of like x squared, but like more squishy. Like steeper at the ends and flatter in the middle. That's not a great drawing, but it doesn't have to be. But the key thing is it's not too tough for us to understand that it switches between decreasing and increasing at 0, and we need to have that in mind when we do the thing. Okay, last time they told us the n, this time they told us the delta x. Our interval is from -1 to 2. That's an interval of length 3. What is 3 divided by 0.75? 3 divided by 0.75, it turns out, is 4. So we're cutting into n equals 4 subintervals. I guess we didn't have to do that division. We could have just started at -1. And counted by 0.75 until we got to 2. -1 plus 0.75 is -0.25. Plus another 0.75 will put us at -0.25 to +0.5. Add another 0.75 and we get to 1.25. Add another 0.75 and we end up at 2. So these are our 4 subintervals, each of length 0.75. To use an upper sum and a lower sum, we need to find what is the highest value the function takes, what is the lowest value the function takes on each of these subintervals. From -1 to -0.25, that's left of 0. And left of 0, the function is decreasing. So, to do our lower sum, let's do the lower sum first. The lowest value that the function will take will be the right-hand value. So the representative point is -0.25, the right endpoint. Here, to the right of 0, the function is increasing. So the lower value will be the value on the left. So here our representative lowest point is 0.5. Here our lowest point is 1.25. 25, not 52. The interval surrounding 0 is the complicated one. What is the lowest value the function takes here? Well, again, it's convenient that this function is easy to understand the graph of. The function has its minimum at 0. We had a whole chapter on finding minimums and maximums of junk, so we can find the minimum if it's hard. In this case, it's not that hard. The value we will use for the lower sum is the value of 0. We need to plug all these functions in, so I need negative 0.25 to the fourth, 0 to the fourth, 0.5 to the fourth, 1.25 to the fourth. We need to multiply them all by delta x, which is here 0.75, and add them up. The delta x's are all the same, so I'm allowed to add them and then multiply afterwards. So our lower sum is 0.75 times all this junk. I type in all this junk. Dear calculator, quit. What is 0.75 times? I need negative 0.25, raise that to the fourth, plus 0 to the fourth is 0, plus what is 0.5 to the fourth, plus what is 1.25 to the fourth. We get 1.88. That's our lower sum. Let's try it again for an upper sum. We're using the same intervals, but we need to find what is the x value in each of these intervals that will give us the highest y value. Left of 0, the function is decreasing. So left of 0, the highest point will be the left end point. So here we use negative 1. To the right of 0, the function is increasing. So the highest point will be the biggest point. So here we use 1.25. Here we use 2. The one interval that contains 0, though, we sort of have to figure out what's the maximum of the function on that region. Let's do negative 0.25 and positive 0.5. The thing is centered at 0. I guess like x squared, the thing is steeper as you go out. I guess maybe you have to plug in numbers to check, but of these two endpoints, the higher one will be on the right, it turns out this time. This is something you can know from getting a basic shape of the graph where you plug the numbers in and you find out the highest point that the function takes is 0.5. It's 0.5 to the, what was the function? To the fourth is bigger than negative 0.25 to the fourth. I raise these numbers to the fourth. I multiply them all by 0.75 and add them up. And then if I factor the 0.75 out, I get this. So our upper sum is 0.75 times what is negative 1 to the fourth. I can do that when it's 1. Plus 0.5 to the fourth. Plus 1.25 to the fourth. Plus 2 to the fourth. I can almost do that one. I'm getting an answer of 14.62. That's the upper sum. That's the lower sum. They are not close to each other at all because these are very thick, chunky delta x values for a function that has very big y values. These aren't good estimates. I guess we might as well get the actual value. The actual value of the integral from negative 1 to 2 of x to the fourth dx turns out to be, hey calculator, can you please graph x to the fourth for me? I guess I'll show you how this goes wrong. If I say calculate the integral from negative 1 to 2, it's going to give me an error. Why is it giving me an error? It's giving me an error because I only graphed the function at 0. Like I graphed this from 0 to 5. That doesn't include all the way down to negative 1. So I need to change my window to go down as far as negative 1. Cool. And now compute the integral from negative 1 to 2. It's 6.6.